Today we start with a bit of show. We'll have a simple demo. RTA Hüsnü Aslan will show you this demo here. This is something related to what you have been learning about motion. We'll see first, we'll see an example of motion at constant velocity on this track. This is also related to what you'll be doing this week in the lab. Okay? So we'll first see a constant velocity situation. You will see the motion here, and you will see the graph of velocity, acceleration, and position all together. And next, we will raise one side of the track, so there will be acceleration. There will be acceleration because of the incline, because of gravity. And then we will again see, due to this acceleration, how the velocity and the position change with time when there is actually acceleration in this demo. Okay, so please pay attention to the demo. And mathematics of the motion that you see is what you have learned to handle with integration and differentiation. Okay, let's go ahead. Okay, what happened here? There is no friction, so once you start the motion, it moves at zero acceleration. The blue curve in the bottom is acceleration, it's zero. At the beginning, there are some slight jiggles. That's because part of the track is not really smooth, so there are little fluctuations. Okay? But roughly the acceleration is zero. That means the green curve, the velocity is constant. And with constant velocity, as the thing moves, of course, the position increases as v times t. That's a straight line with a constant slope, and the slope is the velocity, as you learned. All right? Now, what happens after a while is when the body reaches the end, it is no longer free. It hits and bounces back. So, coming back to the acceleration, suddenly there is a sharp negative acceleration, just stopping it. As you now look at the velocity was constant, and then it goes through zero and becomes negative. That's simply telling you that at the end of the track, the thing is starting to move back. So the velocity has changed with this big negative acceleration. Okay? And when the velocity is becoming negative, the thing is moving back. You see that the position is now decreasing. And the slope is not really constant because the velocity is not constant. Okay? Does everybody get the connection between the motion you saw and the results plotted? You'll be doing something similar in the lab this week. Okay? Now, the next part of the demo is to start the motion with acceleration. Constant acceleration. It will be constant acceleration because the acceleration is due to gravity, which is constant on the surface of the Earth. And because of the incline, aim of the track, it's not freely falling, but it's nevertheless moving downward at constant acceleration. Okay? That's what we will see now. Let's see the motion. Okay? That's good. That was a good example. So, except the problem is, the scale of the acceleration graph is too large, so it looks like it was zero acceleration. It's not really zero acceleration. So if you could change the scale there, we could see, because we are looking for something like 3 or 5 meters per second square, something like that. So just take the maximum down to something like 10. And the minimum to -1 also. Right. Okay, now we can do it again. Okay, let's go. Now you can see that there's a there's a non-zero acceleration. The scale of the graph is wrong, so when you are plotting things in the lab, don't do this. Choose the right scale. But it is a non-zero small acceleration, like something like what? Something like about 1 meter per second square or something. Okay. And due to this acceleration, the velocity, as you see, is increasing. Okay? And then, of course, when it gets to the other end, the whole thing is disrupted and you have big negative acceleration, etc. Okay? So, that's it for the demo today. As I said, this week you have lab. The lab will start with something similar to this, and then you will do other parts of the lab with a pendulum. To make use of the time in the lab and get it done, please be sure to read the lab sheet and complete what's needed before you go to the lab. Okay? Okay. Hüsnü teşekkürler. Now, today we are starting the really important part, the physics of motion. So far we learned a lot of mathematics. Now you have got all the tools, how to write numbers down, scientific notation, vectors, differentiation, and integration. Okay? Including differentiation of sine and cosine functions. So you've got all the mathematics you need for the rest of the course. Now today we will start with Newton's laws of motion. So after Galileo, especially Galileo, who did controlled experiments about moving bodies relative Do I have everybody's attention? Shall I start? Okay. So today we shall talk about Newton's laws of motion. Now we have learned how to describe motion. We have learned about velocity, acceleration, etc. But the really interesting thing is what affects motion. What happens to an object when other objects are influencing it? How the influences from other objects, how the interactions with other objects determine the motion of a particular object. Okay? Now this, of course, is an ancient question, and until the time of Galileo, the notion was that if you apply a force, if there is an interaction, some push or pull on a body, this will just make the body move with velocity. So the effect of other bodies was thought to give just velocity. And when there are no effects, when a body is not being pulled or pushed, then it would come to a stop and it would stay at rest. This was the common notion. Okay? Of course, people understood that this is due to friction, sürtünme. If you have no forces on the body, if it was already moving but there are no forces, it will come to a stop in general. That's our daily experience, that's what we see. And people realized this was due to friction, but they were not able to really analyze, quantify what friction and other forces do, because they didn't have careful experiments. To do such experiments with motion as you see in the lab today, you need a timer, you need a watch, you need to be able to measure time correctly. The technology, the clocks to measure time were not available even in Galileo's time. Okay? He actually realized and invented the working of a pendulum, and that provided the first mechanical clocks. But there was no means to determine time, and also the needs of technology, the needs of people in those early days did not really require a very detailed understanding of motion. It was enough what they thought, okay? So the general prevailing idea was things, when they are isolated, when nothing affects them, no pull, no push, they will just stay at rest. Being at rest is the natural state of all objects on the earth, while objects in the heaven, the planets, their natural state is moving in circles. So there was this idea that things on earth are different, motion on earth is different from motion in the sky. And they tried to understand everything in the sky as motion in circles. And they tried to, they thought what happened to things on earth is nothing if there are no forces. Force means pull or push. If there are forces, forces will cause a velocity. Now, after Galileo's experiments, what Newton realized was something different. So let us now start our discussion of Newton's laws of motion. The first law of motion has to do with momentum. So I'll first make a definition. The momentum of an object is its mass times its velocity. Okay? The first law states if there are no forces acting on a body. Now, we haven't really discussed what force means. So what is meant here is no interactions with any other bodies, okay? Then then momentum does not change. The momentum of this body remains constant. Okay? Now let us see what that means. Now remember, P was m times V, and we learned how the product of two things can change. How do you calculate derivative of mv? Okay? So, Newton's first law says the momentum remains constant, and what that means is the total change of momentum, which could be because the mass is changing or the velocity is changing, this must equal 0. Not always, but in those situations where your body is really free, when there are no interactions, no forces acting on this body. Okay? Usually, the mass of a body does not change while it moves. Okay? In that case, when m is constant, we have m dv dt equals 0. This is Newton's first law. What is dv dt? What is the rate of change of velocity? It has a name. What is it? It's the acceleration. So this means, Newton's first law says, if there are no forces acting on an object, okay, then its acceleration is 0. So the property of motion that is determined by whether there are effects, interactions from other bodies is not velocity, it's acceleration. If there are no influences, no effects, nobody pulling or pushing this body, then the result is not that its velocity is 0, its acceleration is 0. Acceleration is 0 means velocity is not changing. It doesn't say velocity is 0. It says velocity is constant. Okay? So another way of saying Newton's first law is, if there are no forces, the velocity is constant. Now the velocity is a vector. The object is moving in a certain direction. It has a direction and it has a speed. Okay? If the velocity as a vector is constant, it means its speed is not changing. And also its direction is not changing. So, Newton's first law says, if there are no forces, the body moves in fixed direction with constant speed. Okay? And let's remember, this applies to bodies of constant mass. Okay? Now you can think of motion of some objects which, when they are moving, lose mass or gain mass. Can you think of some examples of objects whose mass changes when they move? Yeah, in an explosion. Any airplane, when it explodes, a bad example, splits into two, okay, its mass is changing. But under normal conditions, a jet airplane, when it's moving, its mass is also changing because it's throwing off a jet of gas. That's how it moves. Okay? So in that case, Newton's first law is a bit more complicated because you have to take into account that the mass is changing. But in the usual case, when mass is constant, the consequence of Newton's first law is the velocity of a free object. If there are no forces on this object, the velocity remains constant. That means the object will keep the direction of its motion. It will move on a straight line, okay, with constant speed. All right? Now, how did Newton get to this result? It goes back to Galileo's experiments. Now, Galileo wanted to study motion when there are no forces. If on Earth you do an experiment and it involves vertical motion, that's just fall. There is a force because the Earth is pulling, and everybody knows that. So Galileo studied horizontal motion, okay, on a horizontal plane. But on a horizontal plane, if you push a block and it's moving on a horizontal plane, it's on a plane, okay? So it is interacting with the plane, and there's going to be some friction. We'll discuss friction later on. But obviously, this is not free. So what Galileo did was, he made the same experiment, same mass object, start with the same velocity, on different surfaces. So he decreased the friction on the surface. He put some oil and more oil, whatever, okay? And he saw that when you have less and less friction, it takes the object much longer to come to a stop. It keeps its velocity for very long times. After this, it's not really possible to make an absolutely zero friction surface. So after this is abstraction. From the series of experiments with less and less and less friction, he thought of the limit. He thought that if I could really make a perfect experiment when the friction is zero, that would be a really free body, and that object would never stop. That means it's keeping its velocity, and it will keep going in the same direction, which you already saw in the experiments. So from experiments and from the limit of zero friction, he could deduce that if you could have a situation where the object is really free, okay, no forces, then it will keep moving forever. And Newton realized this as the first law. This is called the law of inertia. Inertia, the Turkish equivalent, Turkish translation of that is eylemsizlik, atalet, which means the body is not changing its state of motion. What is the state of motion? Its velocity or momentum. That is not changing. In the same direction with the same speed. When? Only if the body is perfectly free, there are no forces on it. Okay? Now what happens, the next question is, of course, what happens if there are forces? What do the forces do? Well, if there are no forces, velocity is changed. If there are forces, if there are no forces, the velocity is constant, it does not change. So if there are forces, the velocity might change. But the question is, how exactly does the velocity change? What does the force do to it? Okay? And again, studying experimental results, Newton formulated his second law, as follows. If there are some forces, what does that mean? Well, if our body is not really free, it is being acted on by some other bodies. Maybe just being pulled by the earth, being affected by the friction in the air or the friction on the table, okay, various things, all kinds of forces. If the body is not free, if there are forces, what will happen to the motion? Newton says the body will be accelerated. Now you may say, well, this is just a consequence of the first law. This is not different from the first law, because the first law said if there are no forces, the velocity will be constant, the acceleration is 0. Okay? But from this it does not follow that if there are forces, the acceleration is not 0. Okay? Moreover, if there are forces, the velocity might change, but whether the force changes the velocity, gives you the acceleration, according to a law like F equals acceleration cubed, or 1 over the acceleration or something. Okay, logically that's a possibility. So the second law is not just a consequence of the first law. First law says no forces, no acceleration. Second law says if there are forces, the force gives acceleration. In what way? The force equals the mass of the object times the acceleration. Okay? From now on, I will not write if the mass is constant, because that's the situation in most cases. Later on, we will consider some problems when it is not. So now, from now on, we assume that the mass of the object is constant. And Newton's second law comes from experiments. The same force on two different objects of different masses. You can do this experiment. For example, take a spring, okay, tie a mass to it, pull it, and let's go and measure the acceleration. Now use the same spring, so it gives the same force on a different mass, and measure the acceleration. And one finds that the bigger the mass, the smaller the acceleration, so that the force is just equal to the product of mass and acceleration. The same force on smaller, lighter bodies gives more acceleration. That is an experimental result. But it's a very simple result, but the work could be completely different. It could say, force equals acceleration cubed over mass squared. Okay, it is not. It's this simple force. How do we know this? This comes from experiments. And these experiments, again, have to do with motion, so they were only possible to do precisely, to measure acceleration, etc., when one could measure time. Or when one could carefully devise experiments and realize for a given acceleration what is the velocity, what is the distance, etc. So use the velocity, use the distance count, like in this track experiment, to deduce the acceleration. Okay? So this is Newton's second law, and this is the most important equation of classical science, classical mechanics, because it tells you how motion of objects is affected. Okay? So this is called okay, let me write it again. Newton's second law is called also the equation of motion. Now, we are in a position now, using this law, to define what force is. When a body is being influenced, is interacting with another body, I can see that what happens to the body is that it gets accelerated. I can measure the acceleration. Okay? And that's all any influence with any other body does. It always gives acceleration. And from experiment, I know that for a given force, the acceleration is such that F equals ma. Okay? So this is the way to define force. The influence of other bodies that I call force is just the product of mass times acceleration. Now acceleration, we already know what it is because we know what position is, we know velocity, we know acceleration. What is mass? What is mass? Mass is the amount of matter in an object. I have a box, I fill it with sand, and the more sand I put in there, the more mass this object has. Okay? Fundamentally, of course, traditionally we have ways of measuring mass. We have grams, which is defined as the mass of 1 cubic centimeter of water, etc. These are just practical units. But the reason there is such a thing as mass is because matter is made up of little pieces. And we now know, this was not known in the 17th or 18th centuries. It was debated even in the 19th century. We know that matter is made up of atoms, and atoms are made up of protons and neutrons and electrons. And these things have mass, or we can just say that mass is just the number of neutrons and protons. And electrons are much lighter, but mass is just the amount of matter. That means, what is the amount of matter? That the number of bricks making up the matter, the number of neutrons and protons in this pen, okay, gives the mass of the pen. Okay? Now the unit for mass in our system is the kilogram. So let's figure out the dimensions and units of force. Dimension is a mass, and the acceleration. What's the dimension of acceleration? It's a length over time squared, right? Meters per second squared. The units are kilogram, meter per second square. That must be the unit of force. So we don't need to invent a new unit. It's just the unit of force according to Newton's second law. The unit of force in our system of units is just the unit of mass times the unit of acceleration, which gives us, in the SI system, kilogram meter per second square. Now that's a long combination of units. We don't want to repeat kilogram meter per second square every time. So there's a name in honor of Sir Isaac Newton. This thing is called one kilogram meter per second square is 1 Newton. Okay? It is the amount of force that will give a 1 kilogram mass and acceleration of 1 meter per second square. Okay? Any questions so far? Now what happens when you have two interacting bodies? Okay, so you have for example, you have the sun here. And the earth here. Okay? Now we know that the sun exerts a force on the earth. Because if there were no forces on the earth would just keep moving on a straight line forever. It is not moving in a straight line, it is being pulled by the sun, so it keeps turning around the sun. Okay? So there is a force. Let me call this 2 and let me call this one 1. There is a force that one object, the sun, applies on the earth. But they are interacting, so there is also a force that the earth applies on the sun. When I write Newton's second law to calculate, to understand the acceleration of the earth, I will use the forces on the earth. Whichever body I am studying, I put in all the forces on that body due to everybody else. So I put F12 equals mass of the earth times acceleration of the earth. If I'm interested in following the effect of the earth on the sun's motion, then I will write mass of the sun times the acceleration of the sun equals the force exerted on the sun. So Newton's second law you write for each body, you put in all the forces applied by other bodies on this body. The question naturally comes up, what is the relation between F12 and F21? If two bodies are interacting, is the force this guy applies on the first guy related in any way to the force that number 2 applies on number 1? Okay, that's the obvious question that Newton next asked and formulated. And again, you can check this by experiments. For example, you just collide two cars, two tracks, and see, they collide and they interact, they apply force on each other, and then follow them, find their accelerations. Okay? And with that acceleration, you can figure out what is the force that car 2 applied on car 1. And with the other acceleration, you can find what is the force that car 1 applied on car 2. So this is something that you can answer in a simple way, of course, by experiment. And the result is this. This is Newton's third law. Okay? Now we've seen all of Newton's laws, and now let us see how we use them, how we apply them. If you want to study the motion of a particular object, okay, find out all the forces acting on that object. Let me give you an example. The example is our demo, the inclined plane. This was a very important experiment that Galileo performed many times to really understand the laws of motion. Okay? So let's use that one. So here you have an inclined plane. Here you have a body, some body of mass m. Okay. Now what are the forces on this body? What objects is this body interacting with? Gravity, because we assume this thing is not in space, it's on Earth, so it's being pulled by Earth. Now, I draw that here. Okay. F due to the Earth. Okay. That's what I call gravity. What other forces are there? Slope is not. Slope will enter because when we complete the diagram with all the forces, when we try to calculate them, the strength of the forces will depend on the incline of this, the slope of this incline. Okay, but the slope itself is not a force. We are thinking of other objects that interact with this object. What other objects? Okay, friction. Friction is one of the interactions with what? With the incline. Okay, so here I put friction, and the direction of friction will be opposite to the direction of motion. That's what we learned from experiments. The direction of motion will be down the plane, so the direction of friction is up the plane. Okay, so who applies this? The surface applies it. What other forces are there? Air friction, yes, I can include that in that. Okay, let's now think of this motion. You have to ask really the simplest questions. Okay, this object is on this incline. This incline is solid, it's hard. And when you let it go, the object moves down the incline. Of course, you know. But notice that the object does not move into this incline. Okay. If instead of this incline you had some very soft plastic or mud, okay, have a block of mud, make it into a triangular shape, but it's soft. Put your object here. Part of the motion, in fact most of the motion, will be just sinking into the object. In our problem, with the hard wooden incline, it does not sink into the object. What prevents this? The object's rigidity, because the object is hard. So there must be another physical force due to the interaction of your body with a hard surface. Okay? And what's the direction of that force? It must be up out of the surface because it's keeping our object from sinking in. Okay? Like I'm standing here, and the floor must be applying a force on me to prevent my motion, which would otherwise be in. If in front of me there was a pool and I jumped, the surface of the water does not provide the same force, so I go in. Okay? So for hard objects, in contact with another object, there is this force that we call the normal force. Normal means perpendicular. That's the meaning of the word. And why? Because if you have a hard object, the force it applies is off the surface in perpendicular direction to prevent the motion sinking into the surface, right? So this is the normal force. Okay? And that's also due to the surface. So the surface, this triangular shaped incline, is applying two different forces. One is up out of the surface, normal force. That's because the surface is solid. It's because of the connections between its atoms on the surface. The other one is friction. That's resisting the move parallel to the surface. That's again because of the interaction between the atoms of the surface of the wood with the atoms of your body. They stick into each other. That's the physical reason for friction. These are all physical forces. Okay? And there was one other force that somebody mentioned there, which is also present, which is this one. This object is not in vacuum, it's in air. So due to air, there is also friction force. Okay? Usually we neglect it because it's going to be much smaller. The friction due to the molecules of the gas in the air is much smaller than the friction due to the molecules of the wood or whatever. Okay? But it is there. Now this is what we call the free body diagram. What it means is, decide what body you want to study. Okay, here's the body. Make a picture of the body. Then think carefully of every other force on that body. Not the forces that this body applies on other bodies. Okay, if there's the incline and this body, of course this body also applies forces on the incline. And we can figure those out with Newton's third law. But at the moment I'm not studying what happens to the incline. Okay, so in a free body diagram, I decide what body I am talking about, and I concentrate only on that body, and just carefully think of all the forces due to any body else on that body. Okay, if in your problem you are interested in 2, 3, 4 bodies, for each of them you do a separate free body diagram, and for that moment, just forget about all the other parts of the problem, just concentrate on that body, and put only the forces acting on that one particular body. That's why it's called the free body diagram, because you imagine, although it's not a free body, it has forces on it, you imagine that the other bodies are not there, as if it's just isolated by itself, and you take into account all the forces of the other bodies on that body. Okay? That's how you start solving problems. For each body that you are interested in, you write its free body diagram, and then that will lead you to correctly write Newton's laws. You make a diagram because the forces are vectors, and it is very important to figure out what are the directions of these vectors. That will help you to understand the motion later on. Okay?